SOLIDWORKS has gotten better at some things, but it's been pretty stagnant.
for a decade or so. This is the method we use for top-down modelling, where everything's driven from your top, your driving part, and all your critical features and dimensions are driven off the sketches. So it basically means you can very easily change dimensions later on without breaking the model. If you're building it in a dumb way, our bottom-up method will be a lot more tedious to go and update all your geometry and make sure that the model's not broken or there's not overlap or whatever. The preparation for FEO will take a lot longer. You got to make that decision up front how you want to build the model, and it's going to give the best outcome.
Hi, and welcome to the Engineering Triangle, our new podcast about how to make the best smart machines and IoT as fast as possible. I'm your host, Ayrton Sue, here at Element Engineering Australia. Today is all about CAD, computer-aided design, which is critical to mechanical engineering and product development. I'm here again with Daniel Berti, our senior mechanical engineer, to look at the key CAD software and processes we use at Element. Thanks for coming back on.
No worries. Let's do it.
SOLIDWORKS was the first tool that we purchased in 2010 when I opened the business up. Probably the most mainstream and easiest.
Widely adopted.
Widely adopted and easy for different companies to exchange files and things like that. It's a primary CAD software that we use here at Element. A lot of the things we talk about today will probably be in SOLIDWORKS, but in general, the principles sort of apply to CAD in general, computer-aided design. Yeah, so to start off with, what makes for really good CAD? What's the best modelling or drawing you've ever seen?
It's a very interesting question. I would say that having a logical structure and a kind of well-organised feature tree that makes sense is a big one. For us, having a model that can be picked up even by multiple people is important. There's nothing worse than having something that one person's done that's really messy. They're away, someone's got to go and jump on that model or fix it or whatever, and it's a mess. Every model is different. There's obviously a few ways of going about. There's a few different types of modeling as well. And you kind of got to gauge how much, what the customer actually wants with that CAD model.
Yeah, it can be done in a number of different ways. In our experience, doing CAD using the tools in an unstructured way can lead to fast results for small models. But once you start getting to a bigger model or starting to have multiple people working on the same model at the same time, you've got to have some sort of consistent way of doing things. Yeah. So one of the biggest things that we've worked on or we've developed over the years is just ways in which we continue to do CAD, and then seeing other people's models as well. There are companies that we work with who do great CAD and very similar to the way we do it, which obviously aligns with the way the software works best. Yeah. And there's other ways that we've seen which are pretty bad.
Yeah. A well-organised feature tree is a big one, just being logical in terms of how you lay the CAD model out, your sketches, which kind of define or form the baseline for your model. Making sure, like a big one that we push these days was just making sure like sketches, everything is named so that it's really clear what features are being driven from that sketch. In this case here, we have the model of this tool, which is mounted to a vehicle that we've done for a client. I've got open the driving part here, which just shows how we've laid out the layout sketches or the driving sketches that then form the baseline of the model. So you can see here on the feature tree, everything's laid out quite nicely. You can see this sketch here is just the chassis tray reference, a side view of it, the winch, the different toolboxes that are laid out on top of there. But it's basically easy to follow. Yeah.
One thing that I think a lot of people don't understand about CAD is, especially 3D CAD, is a lot of the time we're doing things in 2D. And we're laying things out in 2D with different planes and things like that. When you're in things like Blender, you're just kind of molding clay. Whereas when you're in CAD, you're structuring a model in a way that is, first of all, manufacturable, which means that you need to have sort of reference planes or whatever. Parametric 3D modeling is the key to doing really good CAD in our experience. So having sketches in this way where we're having one sketch referencing the features of another sketch is the way we've found that SOLIDWORKS works really, really well. If you were to have a feature referencing another feature, so
that is going to change.
That edge or that vertex or that feature changes. We've found over the years that it basically crashes the model, and you can have a lot of issues. So sketches built on other sketches put into a driving part is kind of the way that we have been successful in doing our CAD, and that's what we've seen from other clients and customers when they're doing good CAD as well.
Yeah, so for the most part, this is the method we use. So top-down modelling, where everything's driven from your driving part, and all your critical features and dimensions are driven off the sketches. So it basically means you could very easily change dimensions later on without breaking the model.
And so that one feature that you change in CAD or in the sketch, basically anything that's driven off that, everything else will move accordingly. So it's particularly important for us because if we're doing iterative analysis and simulation, which was basically how we built the business, do an initial design. The initial design is the best that you can think of in your head or you can do in paper and in 3D. And then we run it through a simulation package. We'll find the hotspots. We'll then have to go and change some of the geometry, moving a part in a sketch that then everything else just updates is magical, and it allows us to turn around the iteration time. If we then have to change something and the whole feature tree crashes, then we can't turn around that FEA.
Yeah, so even like thicknesses of plates and stuff, if you define it in the sketches and it's all driven off the sketch rather than you actually using the boss extrude feature and putting your dimension in there, it makes it really easy to go and tweak that.
You can obviously drive off the thickness of that boss extrude feature, but it doesn't always work. So good CAD is a compromise, I guess, but this seems like a lot of work up front, but this is horses for courses. So doing this amount of work here for a complex model, which does need to be changed and improved over time, kind of works for this model.
There's other generic things I would say, just making sure that you're minimizing your feature count where possible. Back in the day, when computers weren't as powerful, you don't want to use 300 features to create something that's relatively simple. You want to try and group things and be, smart about it. A good example would probably be like Magna, even the old Tyre models that we used to do. The side wall text was modelled. We used to use them lines or thin lines, remember? No.
Oh, yes. Yeah. It looked great for the renders, but it was horrific for the feature tree.
But there's different ways you can do things to try and speed up the model overall, making sure everything's like well-defined, in context references, things like that. Just makes your model run better when it starts to get bigger.
Good CAD is a lot of trial and error and figuring out what the program can deal with. On that note, how about the worst CAD drawings? Have you seen some shockers? So just one clarification here. So obviously there's CAD design and then there's CAD drawings. As engineers these days, we seem to do the whole lot. So it's basically coming up with hand sketches, doing the calculations, putting it into 3D CAD, which often is a sort of combination of those things. You're sort of doing 3D CAD as you're doing the engineering. And then a lot of the time our engineering team will actually output the drawings. Some businesses will have specific people that are doing the drawings, but we find that the engineers who are designing things and have often considered the design for manufacture processes involved, they will probably be the best ones to be outputting the drawings. And SOLIDWORKS in particular, we've got templates and things like that make it really easy to put drawings out. We have a specific style that we like to follow, which is very easy for someone to read on the shop floor using sort of isometric views and then different, zoomed in views and whatnot. But the person who's designed it is usually the best to tell that story in drawings. So an engineer these days kind of does the engineering design, the 3D CAD, and usually the drawings as well. So, but yes, we have seen some absolute shockers.
We've seen some shockers. I'm trying to think of a standout. The recent one was a client that came to us with a set of drawings that they asked us to quote for. It was for a spearfishing gun, a custom thing that they had designed, and they had actually made a few batches overseas, but they basically called up and complained that what they received back between the batches had varied massively and there was just no consistency to it. I asked them to send through the manufacture package and I went through it, and it was pretty clear from the outset why that was the case. And essentially it was just drawings that were missing critical features, whether it was the surface finish, the chamfers weren't spec'd properly, dimensions were missing. I just went through the process of just marking up for them, hey, this is what you need to ask for if you're going to do this. We then quoted on doing that here as well. But that was just a case of someone doing the work. They were architects. I don't know what software they used. But they just didn't understand what was important and what wasn't.
Right. Well, that's back to a DFM piece, right? Designing for the manufacturing processes, understanding what the manufacturing process might be and what the people on the shop floor will be using to make that, and then specifying in the drawings what that person needs to know. And which is why having an engineer to do that is it helps so much, because we know what is needed. And it's very clear from the start. For us, process is a big one. Like, I don't know, even with experience, you kind of get good at not missing things, but I
think it's important to still have a process or a review
checklist,
process.
yeah.
So we have checklists, all the things that we kind of check off. So surface finish, dimensions, tolerances are important.
We've come into jobs where we're, extra hands to do a certain part of the job. And I remember one, which was a very similar project to this one. Basically, the model was done in a way, we usually call it smash CAD. To start with, you're just fleshing out the physical features, and the model gets bigger and bigger and bigger and gets slower and slower and slower. So for us to have any useful impact, to be able to change designs or create drawings, the model was so slow that we had to basically go back and redraft it or re-CAD it using a top-down modeling technique.
So that was the same thing, right? It was basically going through the design, analysis, optimization process, and the geometry kept changing.
Yes.
And every time we would try and change something, or they would, the geometry would break, essentially. And that was the reason it wasn't built the way we would have built it, which is using this top-down method, as is shown here. But
it's horses for courses. You got to look at the scope of a job and figure out, is this something that the customer can get some quick wins with a single design process with no iteration, or are we going to full production drawing version?
Are they even building the model? Are they using that for manufacture, or is it a marketing thing, or just analysis even, which happens in many instances where we're using a model that's given to us. The manufacture drawing's not even done on our side.
Yeah, there are definitely some shockers. You can definitely use CAD the wrong way. How does CAD fit into our product development process?
Developing any product, we would always advocate start with sketches first. CAD is great. It's obviously the first step to getting a 3D model done, and then subsequently, doing your manufacturing drawings. It also is what allows us to do marketing content. So you use your CAD model to do renders. We use it for analysis. When you're sending parts out for manufacture, CAD allows you to output your DXFs for like laser cutting, engraving, machining. We use step files, things like that. So without CAD, like the old school way was to draft it all on paper. It was a much more laborious process. A lot of time the drafter would do all that, and then it would get transferred to CAD, but it starts in sketch form.
Yeah, we're very big here, and we really advocate for this, is doing as much as you can on pen and paper onto the whiteboard, but that only gets you so far. Even if you were to measure things out and flesh things out, going to 3D is the next step, and 3D will basically flesh out what's going to clash, what's going to fit, those sorts of things, and you'll get a lot of work done there. The next stage would probably be to analyze it and actually understand what the stresses and structure are, and then from there you're going to have to be iteratively changing things. So CAD is integral to our whole product development process, but we don't jump into it too soon.
Yeah. And even on that note, SOLIDWORKS is our base, a CAD package that we use for the design and getting the manufacture package out. There's also there's other CAD packages you can use for things like preparation for FEA that massively speed up the process. So now, for example, when we do FEA, it's a lot quicker for us to take the CAD that's already there in SOLIDWORKS, and we take that to another one called Space Claim at the moment, and allows us to really quickly modify and simplify features.
Previously, we were going back into SOLIDWORKS, and we were making a SOLIDWORKS variant of the model, which would basically do that simplification, but the CAD program itself wasn't as good as these new programs.
It's integral across, from start to finish. And the other thing as well, actually, with CAD, so for the last few years, we've been using SOLIDWORKS PDM, which allows us to collaborate as a team on one project. It's not really possible without having PDM to do that within SOLIDWORKS. It also allows us to standardize the review and approval process as well, all within that software package.
Your team's grown a lot in the last couple of years, and before that we didn't use it because we would only ever have sort of one, maybe two people at absolute max working on a project. So having it on a shared folder on a drive was okay back then, but PDM is kind of integral now to a larger team.
Yeah.
Again, horses for courses. Don't go spend the time and effort on PDM if you don't need it. But it does obviously give you a lot of advantages if it's easy for you to integrate into your workflow.
Yeah. Even I guess the other one would be probably even the fact that it ties into the electronic side that we work on as well. So we're able to work alongside the electronics team.
Yeah, so we've got SOLIDWORKS Electrical, but we're doing
Co-Designer?
Altium Co-Designer. So Altium Co-Designer with SOLIDWORKS has become really powerful. I've used it since it first came out, and at first it seemed to be really good, and then something went wrong, and then we were basically just importing step files of the electronics again. That seemed to become hard work, and then the last 6 months or so, something's happened, something's changed, and it just works. So you can basically bring in an Altium file, use the SOLIDWORKS co-designer. It will basically make a SOLIDWORKS model of exactly what you've modeled up in 3D, and then you drop that 3D model into your mechanical model, look for your clashes. You can then move things around within SOLIDWORKS that then gets synchronized back to Altium. That's amazing for our electronics workflow. For a sort of more electrical, where we're doing control boxes or routing of cables, SOLIDWORKS Electrical is great for that. So we've got a license of the SOLIDWORKS Electrical package now, which allows us to basically really quickly bring all the different parts into a control box. It might be integrated with a vehicular solution or something like that, and we have to basically route all of those cables. We can get cable links, we can get a bill of materials, all that sort of stuff. So it's really nice. What software do we use at Element for creating CAD models and drawings, and why? The world is changing.
This is an interesting topic. We use SOLIDWORKS. It is probably the most widely adopted software used in the world, I would say. There are other products out there. For us, it was a case of like when I started, everyone was pretty much learning this at uni. It was what they used. So for us, taking on graduates or anyone new, everyone's pretty much trained in SOLIDWORKS anyway. Any mechanical engineer around knows how to use it. In our part of the world, part of the world. For us, it's important that the CAD packages, it's probably easy to use, has a nice, clean interface. Obviously needs to have all the capability in terms of like features, being able to do everything from simple to complex surfacing, and do that in a nice way.
Cost and time effective.
Cost and time effective is a massive one. That's where we're kind of always on the lookout for other options. SOLIDWORKS isn't the cheapest option around.
But it does the job, and it's got all those features to be able to do it. And lots of people in our industry, even our international clients, are using it, and suppliers which we're interfacing with, sending drawing packages to. If we need to send a raw SOLIDWORKS file so they can see all the features and they can potentially change things if they need, it's right there. So there are cloud-based solutions. Onshape is definitely something we've been looking at over the last couple of years. Onshape was actually developed by the guys who originally developed SOLIDWORKS and so sold out to Dassault Systems, and then developed Onshape as a new solution. It's got a great workflow. For us, it's picking it up. It's picking up that workflow and changing our whole business towards a new product. So it's a big process for us, given the team, the size of the team. We have used it in smaller projects so far. It doesn't have all of the features that SOLIDWORKS has. So for us to give the customer the best time and cost, SOLIDWORKS is still our chosen tool. Yeah,
it's tried and tested.
SOLIDWORKS has gotten better at some things, but it's been pretty stagnant
for a decade or so.
I think the first license that we owned here was 2010. Seemed to be like a real improvement in the workflows and capabilities of SOLIDWORKS by about 2014. Back in the day, I was the one doing the big tyre models, very complex tread patterns. We were doing welded steel structures for truck trays with hundreds, if not high hundreds of parts. Parametric dimension-driven models back in 2010, where you'd have hundreds of parts and you change a couple of sketches and the whole drawing package just pops out. It was capable of doing that then on the computers back there. But it seems like these days the capabilities haven't gone too far, and you kind of need these bloody supercomputer laptops.
They've basically like locked in the fact that you need to change your hardware every 2 years, 3 years to keep maintain performance.
I don't know why.
Which is my main gripe that I have. It's very frustrating when you open a model that you opened 10 years ago on a computer that was 10 times slower and it's no quicker or worse even. You wonder why.
If SOLIDWORKS could tell us why, that'd be great. I'm pretty sure everyone in the SOLIDWORKS industry or ecosystem is asking the same question. But at the end of the day, if you keep your hardware up, it has gotten better. The graphics is fantastic. There are all of these other little features which we pay for as part of the licensing, which no one uses. But it'd be great if we just put more effort back into the core that makes this thing awesomely parametric and give us the performance that we were having back in 2014. That'd be great. But SOLIDWORKS still does a job, and we love to hate it.
It works in our computers. We've got decent computers, so
you have to. You've got no choice.
Just have to budget in the upgrade next year.
What would the ideal CAD software look like?
So I would say a good, simple, easy to use interface. Obviously 3D modeling capabilities is a must. Being able to do everything from simple to complex shapes, just having all the features there to be able to model what we want to use. So for us, we use a lot of sheet metal, we use a lot of weldments or do a lot of structural members. So SOLIDWORKS works very well
Yeah.
for that. Super simple to use. I know these days we're more reliant on using like even 3D sketches, which simplifies again. So the model that I've just showed before, that's all done. A lot of 2D sketches. We probably would even use 3D sketches or a combination now to make it even easier to use. And probably even the design, like access to the design libraries that they have as a baseline. So you've got all your standard fasteners.
Probably connected directly to certain manufacturers as well, or suppliers. It can be done, and it is done at the moment, but you have to have different snap-ins or whatever, and each snap-in's kind of different. So a standardized way of bringing in parts would probably be great.
There is a nice one that we use, which is the Magna Tyre add-in, which is really nice. It's just a tab that you have in SOLIDWORKS, and you can just type in a part number through their catalog or go to catalog directly, and you just download a part and just drop it straight into your assembly. I saw
a meme the other day saying that Magna Tyre is holding up the whole of the US innovation ecosystem. It's helping us here in Australia as well. We buy stuff from Magna Tyre, or we integrate it into our models because it's so easy to find.
And it is so well laid out.
Yeah.
Like that, yeah,
they've got everything there. Which is great. And I guess the multi-user ecosystem as well.
Yes.
Where you've got multiple people working on the project.
Another one that's important for us because we do a lot of simulation is understanding motion kinematics. So SOLIDWORKS does have some nice features for that, where you can basically output forces for different ranges of motion, and you can run that so you can optimize your kinematics of whatever it is you're designing.
That's come a long way. And that has come a long way in the last couple of years. Yeah,
so that's quite easier to set up all your mates and actually run that. Visualization and rendering is another one that's quite integral for us. They've now got Visualize as part of their integrated rendering package, which is nice. It's very easy to use, and allows us to provide nice renders to clients throughout the working stages of the product development lifecycle. Yeah,
certain clients will pick up things better from a visual render that looks photorealistic than they will from a CAD model, which is important. Onshape has some wicked new features as well, which is more like a Git style revision control system where you can see other people working on the model in real time. It's cloud-based. I'm still not sold on the cloud-based. I'm old school. We've always had, big machines with our own servers to run the files and whatnot. But also then you've got a workstation which has got your own onboard graphics card. I haven't played with Onshape. You have.
We benchmarked it. It was definitely better than I thought. The cloud performance, I think they used Amazon. It was also better than I thought.
Was it as good as a desktop SOLIDWORKS?
I would say for the most part, yes. For most of our models, yes. And it was just nice knowing that you could be anywhere. Yeah. And it was consistent, right? Like for me, I'm a laptop user, so the card I have on this is okay. Yes. But for me, it would be better using there. Yeah. Maybe not someone with a dedicated workstation as such. Probably the only one that we tried that it didn't really perform as well on would be like Magna. So some of the tyre models that we have.
So
that's
full surfacing geometries, very large, multi-patterns.
So it basically auto scales the quality based on the model. And you do get some control over it, but we couldn't get it to look as good as SOLIDWORKS.
That was a while back as well. So
we should try it again. Ask him for another trial or even get a license and you'll see.
A lot of the CAD providers are trying to go cloud-based. I honestly don't see it yet. We do have an infrastructure here that we've built up over many years, and we've got perpetual licenses. So that's things that we're going to stick with until we're kind of forced. And we are kind of being forced down that path of going to the cloud, which is neither here nor there. It's the way of the world. But if it gives us a substantial improvement in our workflows, we'll do it. But at this point in time, I can't see it. And from all the marketing hype, we have marketing people coming out from different SOLIDWORKS vendors. And unfortunately, we often know a lot more about the product than they do. A lot of it's marketing hype, unfortunately. We're in it all day, every day. So we understand the product. And if we can see that really big jump in user experience for ourselves, which is going to give us lower cost to the customer and decrease time to the customer as well, we'll jump on it. But I haven't seen it yet.
Yeah, I'll be inclined to agree. We're always thinking about it because for us, for the mech team, we're always looking ahead. No, not that you're not, but we're obviously the ones on the floor that want to kind of show it and demonstrate it. And it's cool when you find something new that does something better than what you've been doing.
It is a bit of a letdown, right? Like Altium, we got on board with Altium quite early on, I don't know, more than 10 years ago now, and there has been a successive incremental improvement every year. There are new features that you use every day that are always coming out and improving. SOLIDWORKS feels to me like every time I jump back on it, I'll jump back on it for a couple of months to do conceptual design sort of things. Feels the same as when I was using it in 2014. That to me is a bit disappointing, right?
Yeah.
And I'd love to see leaps and bounds improvements. We are absolutely advocates for it, but it's a love-hate relationship, right? Like, what do we keep paying for? If the 2014 version worked with the 2014 PC,
why couldn't we keep that? And
well, obviously the 2014 PC is going to die, but it's just one of those things. Love-hate relationship with the vendor. I'm going on a bit of a tangent rant here, but having salespeople tell us absolute bullshit about SOLIDWORKS, we've just seen it for so many years. Like, tell us exactly what this thing is. Understand what the product is, because we're on the floor all day long, every day with it, right? If you've got that level of use with the product and you see the leaps and bounds, sell it to us. Don't sell us the dreams of all this other crap that we don't use. You know what I mean?
Yeah. I do remember about 3-4 years ago getting told at one of the SOLIDWORKS events by one of their guys that he just asked me what simulation software we use. And he basically was just ranting to me about how their SOLIDWORKS simulation tool is now better than ANSYS. And
they've been saying that for years. You know what I mean? Like,
but it was just complete bull.
Yeah. It's typical. Back in 2010 or whatever it was, they were saying to me that Abacus was going to be integrated into SOLIDWORKS, and it's just crap. It's bull crap. So, we don't need that stuff. We don't need that as an industry. We need everyone on the same page so that we all understand it, so we can do better for the customers, better for the innovation ecosystem. We can all make each other better by having these SOLIDWORKS users groups and things like that. That's kind of fallen down in the years here in Perth anyway, because I think some of the SOLIDWORKS resellers were getting involved and sort of making it more of a sales pitch rather than a users group. I'd love to be able to get those things together. And I see that there's some very good user groups around the world, especially on the East Coast. Everyone's supporting everyone to understand what the limitations of the product is, teaching each other how to do things. The app developer meetup that we have here is exactly that in software land. And really, we shouldn't be competing against each other in those domains. We should be helping each other, because the innovation ecosystem needs to grow so that we can all benefit. Sorry for the SOLIDWORKS rant. How can we generate CAD models quickly?
You need to understand what the CAD model is being used for.
Yeah.
It's a different process. If you're going to do something complex, it's going to go through multiple design iterations. And obviously, if you're intending on outputting a manufacture package, that the path you take to putting together that CAD model is very different to if you're just trying to smash out something quick that's for visualization purposes only. We, over the years, have built up a lot of template models, if you like. We've got a client that we do a lot of tire renders for. I believe in the past, some of those have been used for production where everything's got to be accurately modeled to the kind of millimeter. Other times they're just for renders. The tact we take is a little bit different for each. For things like transport frames, for a lot of mining equipment, which we've done in the past, we've got like a suite of template models that we might, when we get a new one, we'll go through that template model list and look at the kind of most similar one. And these are models that have, fork tines, tie down points, lifting points. You're able to leverage something that's kind of almost there, even to the state where the drawings are somewhat done, and you might be able to speed things up and obviously keep costs down for the client. Yeah, Smash CAD, as we said before, if you're doing fast CAD models, you might not need to worry so much. If you're never going to have to pick that model up again, you kind of just smash it out.
So that's when you're trying to understand the 3D geometry, basically. So you're taking something from a sketch on paper or on the whiteboard to basically fleshing it out in 3D, understanding what that may look like. It's not going to be manufacturable, and doing it kind of once off. Yeah. That's it. And then if you need to go back and tweak something, really you should go back to doing a proper top-down modeling technique. Yeah. And again, the top-down modeling technique could be more simplified, or it could be really, really detailed so you can get specific features out.
Sometimes we might adopt that approach where, we do like a smash model relatively quickly. We might need to do some analysis on it. We might then move it to our interim space claim for FEA prep. There's some pretty nice optimization tools in there that are it's very quick to do a parametric analysis with. From there, we might optimize and iterate the design, not worrying about how it's done too much. Then from there, we'll take that final FEA model and then we'll kind of go back to SOLIDWORKS and we might do it all properly. Particularly if that client is going to use that as a manufacturer package that may turn into a V2, V3 later down the track. That was the case with this model here.
This is obviously a production grade model, and you can see the feature tree is pretty messy. This model's kind of not crashed, but it's got some issues with mates and stuff, but it's okay. It's okay to be like that if we got the customer to where they needed to be.
in this feature tree, like, even the way it's broken down, so everything is named. We've got like a part numbering scheme that we follow, all jobs across the business, unless a client has their own scheme that they want us to use, and then we would obviously adopt that. Here you can see we've just, it's another good modeling practice is just making sure you're using assemblies or sub-assemblies to segregate your different modules or components that are kind of going to be manufactured as a standalone part or system.
So the driving part basically has a bunch of sketches that are driven off other sketches and define basically all of the geometry of an entire model. And then from there, we'll basically build up parts within this assembly model or sub-assemblies of parts. And each one of those sub-assemblies, to do CAD really well, especially in a multi-user environment, you should be segmenting an area of the product into a sub-assembly, and the driving sketches should really be defining just the outline of those things, so that the top-down modeling is kind of defining the overall where things are, and then the sub-assembly may have some specific sketches which is detailing things within that.
Yeah, so in this case here, we're essentially doing the layout for all the different toolboxes, all the components that are being fitted to the truck. So we had to have the truck model. I think we, at the time, had to measure everything on site. We had a couple of our guys actually on site building the model up alongside them.
So measuring with a tape measure. Laser scanning has one place as well, but measuring with the tape measure definitely has its own place as well. You can go and take your tape measure, string line, some levels and set squares, and get a model up really, really quickly. Going to the extent of doing a scan and then having to import the point cloud and things like that can actually create more work, which is, again, what the customer may ask you for, but unless it's got some sort of positive outcome for the end user, it's going to be more costly and more time. So just going and measuring things with pen and paper. We have measuring bags in the office. The guys take their pen and paper with a bunch of different tools, and they basically go and measure the thing and get a model up real quick. And you're basically taking a laptop, putting it next to what you're doing, measure it by hand, and make the model as you go.
Once we've got the truck, the tray, everything's modelled correctly, we can then start to play with layouts. So obviously the client will then communicate to us all the different modules that they might have had some preliminary designs for at the time. That's my recollection. We would then lay things out on the truck with some input from them until kind of we had everything in the right position. You would do all that in using just very simple block sketches, just using rectangles, for example, that represent the overall dimensions of your different toolboxes or whatever that were then being placed. And
anything that crosses over between sort of a sub-assembly and the main assembly. And then you would detail the interfaces, sort of like bolt holes and things like that.
Exactly. And then we start to look at mounting. Once that's all locked in place, we will then go in and create our different sub-assemblies in their correct location.
And then you can detail them directly in the sub-assembly.
Exactly.
So someone who's involved in that is not going to have an impact on the whole model, or the whole model is not going to have an impact on their particular sub-assembly.
So then you can have 2-3 people working on that same model, each on a different sub-assembly at any one time. And that's it. And that's how you get more complex jobs done more quickly. And that process works very well with PDM.
You are using a gaming laptop to run SOLIDWORKS, which is not ideal, but for your workflow, it works, right?
Yeah, exactly.
This was one of the projects where we used the parametric modelling.
It was full like parametric with equations and everything, so it was it was very intelligently built.
Cylindrical water tank made out of very light sheet metal with a sort of standardised bolt pattern on either end. This particular customer wanted to make different size models. So we basically created a parametric model. This is from 2010-ish or 2012, something like that, when you first started, Dan. It took us a while, but basically you create a top-down model which defines the overall geometry, so that you can see there that's different diameters, there's different parameters that we've put in there, and they're all driven. So one of them might be like the panel length, one of them might be panel width, number of panels high, panels low. You can basically use these drivers as an input to then generate a whole model. So using the same standard panel sizes with standard bolt patterns or whatever, you can make an infinite number up to a certain size of these things. That's what I've done, back in the day for a few customers where they were building production versions or different variants of the same design. So we did it with DT HiLoad Australia. We did it with these guys, Boss Bros, who became a different company afterwards. And instead of redrawing every single version, we basically go into here, change those particular parameters. The model then updates. Hopefully, we can pump out drawings directly from that. A lot of the time there would be some cleanup involved. There might be things that may break.
But it was relatively quick. And I remember, I think the process might only take 1 to 2 hours.
That's right.
To do a full size change, so larger diameter, taller. I think there were instances where the ladder might not have even had a ladder or something. I can't remember exactly. It was kind of almost a template model. So we spent the extra time up front to then go and configure as many of these tanks as needed.
So that's an investment piece. So say the first one takes you 10 hours to make a model. If you want to go into the second one, it might take you 8 to 10 hours to do the next model. To do a parametric model like this, you might be talking 40 hours of investment work into developing the parametric model. You basically make it once and then you try and do another size. And when you try and do that another size, something will break. You go back to the original parametric model, you change and improve it, and you try and do 2, 3, 4 different variants. Once you've got the parametric model working well, each change is an hour or two. Depends on the size of the model, the number of, use cases you want to have. For this customer and for, say, DT HiLoad Australia, there was an infinite number of variants of different sizes. DT HiLoad Australia would specify a specific truck tray, which would be a certain width and height to take a number of loads from a huge digger, or a specific amount of ore with their known density to be able to maximize the payload of the truck. So you could be 50 millimeters wider or taller between models for different mine sites or whatever. When I first did it, it was months of work. The first model that you make might be a month of work, and then you spend a month or more to try and make it parametric. Then you spend the first 2 or 3 or 4 iterations after that. You're using it to create production drawings, but you're also going back to the primary parametric model and you're improving that. But the team in-house, DT HiLoad Australia, they then took that model and then they continued to improve it year on year. Those sorts of models can become arduous as well. They can become overbearing if you're not working on them all the time. If you're going to do something like this in parametric, you've got to continue to improve it, and probably like this, maintain it over the years of different SOLIDWORKS versions and stuff.
When you're doing it, you have to understand what the model is being used for. And even when you're doing that, dimension-driven parametric models, you still have to have an understanding of what you think is going to change to do it in the most efficient way. And then you make sure that is all captured within your sketch, your layout sketches.
This one is probably one of the ones which is more a productionization system. And you can do it in SOLIDWORKS, you can do it in other parametric CAD modeling softwares, of course, but there might be times where you just need it to flesh out things you can't do on paper. And you're just doing a 3D model and you're doing the smash CAD, like what we said. One of our clients is Magna Tyres, who manufacture big industrial tyres. How did we use smash CAD to help them optimize their products?
Magna is one of the heavier models that we deal with, like just graphically. There's a lot of like small features. The purpose of it for us has mostly been to provide renders as marketing content that look really good. Obviously are indicative of how they're going to be made as well. For us, knowing that it was going to be something we're going to be doing lots of, it was important that we establish a good, baseline set of sketches that form the base geometry of the tyre for us to then build the kind of tread onto or whatever.
It's good to see my sketches that I did probably in my thesis.
They're still there.
They're still
there, at least in this model.
Magna Tyres is basically one of our first clients back in 2010. It's one of the reasons why I started the business was I got busy with DT HiLoad, and also Magna Tyres approached me from my previous tyre engineering work that I was doing with a local company. But I did my thesis on tyre design, which was the heat build-up within the tyre generated by the different compounds and how the casing affects the tyre deformation, and then how the tread pattern basically dissipates that heat due to convective cooling, effectively air convective cooling. This is a radial tyre, which basically has steel casing wires that go across the tyre and go around the bead. You can see down the bottom there. We're modelling in the rim and the flange of the rim, the bead and the casing wires that go up and around the bead and how they're going to interfere on the bead. Then we model in the other radial plies, which basically hold the air pressure in place. And then we even model in the different rubber compounds within the structure. From there, we then also model up the tyre tread pattern on top. And the tyre tread pattern is what basically dissipates the heat and gives you the traction and makes the whole tyre work. This model is kind of done in a way which you could produce a tyre mould and casing design from this, but we're using it specifically for tyre renders, which is what this customer primarily wants, although we have done a lot of simulation, some certification for some of these tyres, and some iterative improvements to different casings and the tread patterns over the years.
So you can see here we've just started, we've got our layout sketches on this front plane here, which basically form the base of the tyre.
This is basically the rubber compound that makes up the casing, but not the top tread piece. We're then starting to put different features into the model.
We've essentially done an extrude of, I guess, the
main lug pattern.
The main lug pattern, which then gets patterned around the whole tyre. We then cut some of that away, which actually forms the outer profile of your tread.
This is one way of doing it. There's other ways of doing it.
Yeah, so I think the way we do it now is different. This is the old way, I'm pretty sure.
Yeah, this is a more simplified way of doing things. It looks good enough. And it depends on the lug pattern as well. If the lug pattern is quite chunky, then this way of doing it, it's not really the way we want to be doing it, because when you do an extrude, you're going straight down, but that's wrapping around the radial profile. Most of the lugs will be radial from the center out. Now
we use some wrap. I think there's a wrap feature that we use with surfaces, and it's a different process.
But again, horses for courses. This is a way to get a model out that would satisfy some really nice looking renders.
It's also quite easy to follow as well. It is very simple. The other one's probably seems a bit more complex just in terms of the features that get used, but it makes sense.
This model is behaving quite nicely on your gaming laptop.
Yeah, it's better than I thought. So you can see there's a bit more detail with the cuts here and these little ridges here. There's no fillets in there or anything yet.
Cutting away different bits and pieces. Just building up the model.
Then we go to adding in fillets.
Fillets are usually really heavy.
So I think even the process now is different because we're just doing that section. It's working on a section first, and then we complete that before we do the patterning it. Whereas now the features are being applied to, I think, everything. The whole model. I don't know how it's running.
Although this model is behaving a lot nicer than the other model we bought up before. We're putting in some of the detailed features that would make a model look realistic. You get used to having a lot of sketches in the way and things like that. Sometimes it looks like a mess of things. Often when you're doing CAD design, because you're the one working on the model, you understand where all these sketches are that are driving different features, and it doesn't get in the way. You actually want those sketches to be in place for you while you're working on the model. To other people, it may be overwhelming. So when that person comes in and all those sketches are on, it's very overwhelming when you see all those bits and pieces. So making sure that the model is structured in a way that you can turn those things off or hide them, and then the person can roll back. They can then uncover things and discover how you've built the model. That's pretty important to CAD modeling in general.
So this would probably also be a very good example of a model that maybe they're doing it now, but even like in terms of naming or grouping the features where you would probably do that. I know when I started, it was only really 2 or 3 of us doing these. It was kind of one at a time, really, because you were doing it first. Then it became maybe Ben, then myself. And I would just pump out, 50 over the period of whatever, a couple months. So you're kind of not really thinking about other people using it.
Well, you're giving the customer the best bang for buck.
Exactly.
Right? Like we haven't named all of those particular features and stuff. And when you're doing it, it's quite easy to name those features as you go if you get into the mode, but it does take time. And if you don't need to,
doesn't matter. Now, for example, we do have like a document. It's a few pages long. It just gives you the steps and like what to do. And things to like pay attention to in terms of whether it's dimensions or sketches or whatnot, all the way through to getting the model ready for rendering. Because even the sidewall now, there's like 3 different variations of the sidewall text and how they want that displayed on the render. This one you can see it's just like white extrude. Whereas they got a version where it's like striped, not white. It's the same color as the rubber.
But that's a fairly simplistic model. The logo was a hard thing back in the day. This was taking an Adobe file, Adobe .ai file, Illustrator file, and then basically having to bring it into SOLIDWORKS and then create that feature. So if you zoom in on that, you can see just how much detail is in that. It doesn't have to be like that, but it works and it looks really nice when you're making renders.
But the same process again to keep things moving or the model working quickly. That's done as a separate part or even assembly with the text, and then brought in after. So splitting your model up into modules or sub-assemblies in a way that it can be worked on as well is important. If you were to try and do this all in, say, I don't know, one part or even working on it live through the assembly interface, it would be a nightmare, well, at least with my computer. But
most people's computers. We help DT HiLoad design and optimize huge dump truck trays used in mining operations. How did scalable models help us generate fast production drawings for them? The model we've got up here is one from years and years ago, maybe 2012, 2014-ish era. This is actually an underground truck tray which we were creating at the time, and it was very successful. We went out, and myself and Frenchie, Ben, who was the first employee, Dan was the second employee for Element, went out and measured our underground truck using measuring tape and different hand tools and came up with a model. We basically simulated it using Abacus back in the day and iteratively improved it and got rid of all the hotspots. This truck tray went on to serve thousands of hours, as far as I understand. We only had one problem, which was at the back of it, which the angle of repose, or the angle of the plates basically had some hang-ups. We had to put another hang-up plate in the back. But this model here is a model that we developed for FEA at the time, and then it became a full production model. And this is one of the stages of production, which I think we're trying to show different parts of the structure that need to be installed at certain times. And then I think if you zoom into the back there, Dan, you can see different lugs. So on that red piece, you can see, so those lugs there may have been used to actually hold that piece, maybe for rolling that plate or for assembling that plate. So this is a stage of the production process that we model into CAD, and then we will modify as the next sort of configuration, which then goes into the next stage of production drawings. Opening it up from back in the day, it still works. This looks like the full production model. We did things a bit differently back then. The naming schemes were a bit different. And obviously we just opened this up from an old server image. That's the top level assembly. You can see in here we've routed specific lines that need to be routed around. This is a proper top level assembly with final installation, I guess. And we would have been creating drawings of this final installation. And this is how we would create production grade drawings of each stage of the manufacturing process, basically nesting what new parts would be added on to the previous part. So in this stage here, it looks like we're bringing in a floor subassembly, a sidewall or a wheel arch assembly, 2 wheel arch assemblies. We're bringing in 2 sidewall assemblies, and we're bringing in a front wall assembly and some individual parts. So if we go maybe back to the floor assembly, there would be an assembly drawing done at this level for bringing all of these subassembly parts together.
So even, I guess, building the model, you have to understand when you're modelling something as well, how it's going to be built.
Yep. In this one here, we're bringing in a rolled floor section. That looks like a subassembly, so it's basically a couple of parts that are rolled and then welded together. And then we're bringing in a beam assembly, 2 beam assemblies, 3, 4, cross beam. So these are all sub-assemblies that would, again, have their own drawing pack. And then the other part of this as well is the jigs and fixtures. So a lot of people don't understand or don't appreciate a lot of the time. When you go to production, you'll need to make a fixture that may hold all of this in a particular spot. When you start to weld it, it basically stays in that spot. You need to be able to climb on it. People need to be able to use cranes and lifting jigs and whatever to bring these parts together. There will be jigs and fixture models that will be on top of these as well, and they'll become part of the drawing package for the customer.
We worked alongside DT HiLoad, even through the whole process, basically with the guys on the shop floor.
Absolutely,
as well, make sure that everything could be done in there.
Yeah, there was a specific phase. So we did the FEA and we come up with basically the design, and then we engaged directly with the workshop manager, basically, and we went through each individual sub-assembly and said, okay, how would you like your fixtures to be created? So they were literally hand sketches or up on a whiteboard. That's often an overlooked part of engineering, is engaging with the guys who are going to make it. Like, you really have to appreciate their skill and the time and effort that they're going to take. If you just assume something, you're not going to get a good outcome. Most people are probably not going to enjoy working with you, first of all. If you do get the buy-in from the guys on the shop floor, they're going to love it, and they're going to want to put their pieces of IP, ideas, experience, all those years of experience on the shop floor. You should be learning from and giving them what they want. You can then engineer it so that it's the best possible outcome for time, cost, weight, whatever, and do it together. Do it a collaborative effort. A lot of young engineers don't really appreciate the experience and wealth of knowledge that comes from these, the fabricators, machinists, suppliers that you're working with. You really should be engaging in a real collaborative way. A
point probably to mention in terms of like doing things cost effectively. So even doing manufacture packages can be very time consuming to do. By the time you go and do drawings of all your assemblies, your parts outputting DXF, step files, whatnot, if there's any chance that things are going to then change after you've submitted that or whatever, it can be a bit of work to go and do it again. So even for us, again, that collaboration does really help because you're kind of all agreeing on like the assembly or some sub-assembly or overall design before you go and work on your manufacture package. That's kind of been the case with a lot of our clients. Like most of the people we work with, we're very integrated with. It's the way we both prefer to work, really, because they get what they want.
You have to be. You have to appreciate their experience. We're not experts in their field, and there's so many times, especially in FEA, when we'll basically come back to a customer and we'll say, "This model is showing us hotspot here," and they go, "Actually, in the field, in our the trials we've done or whatever, we get a crack there," and you're like, "Oh, okay." You'll understand why and what the situation is that's causing that. The collaboration is absolutely integral to doing engineering cost and time effectively and just doing things collaboratively. I've seen a lot of head engineers, right? And engineers that think they're better than these people on the shop floor or their clients or whatever. Definitely not the case. We are the ones that are often learning on the job as well. This is a big driving part that is done in a kind of an element old school way.
But same thing, right? Like in terms of logic,
everything's
neatly named out, everything's named, so it's very easy for anyone to pick up. Because if that was numbered, you would be a minefield. Yeah.
One thing that we do now is obviously we put them all into folders and we kind of group them together much nicer. Yeah. There's all these different chassis sketches, the measurements we took on site, which are basically defining where things are. We're just doing them in certain planes and creating a model just from tape measure and ruler. Then we've started to do our layout sketches, and these layout sketches are the ones that we can really drive the whole product with. Actually, this one's replicating the OEM dump box. And then we've got the different profiles. This is a new feature, which is quite overwhelming, showing all of the different references. Yeah. Wasn't a thing back in my day.
Troubleshooting, yeah.
I feel like an old fart saying that. Different beams, doing them in different planes, basically. We're setting up different planes from sketches. It's how to make a robust model in SOLIDWORKS at least. We worked alongside KLS's team to model and engineer the Epiroc OreSight downhole logging platform to gather accurate high-resolution data from drill holes for the mining industry. How do we approach that project?
So the project started back then through a contact that we had. He needed some help initially with some analysis work that he was doing when he was working for a client doing this project at the time. So we assisted him with doing the analysis work, doing some of the design refinement around those kind of subcritical components that we were analysing. From there, I know we kind of learned a bit more about the project, which is basically just a downhole assay tool, essentially a logging tool for drill holes on different mine sites. And it's basically just a big sensor that they send down the hole and gathers data as to what compounds, compositions. They'd basically come up with this idea of making an autonomous version of that. I think prior to that, used to do like coring or something, and it was a bit more expensive, tedious process to doing that. They were in the initial concept phases of this project of having this tool, installing it or mounting it onto the back of a roadworthy truck, if you like. They will then take that to site and run the tool on all the different holes. Kind of worked with the draftsman at the start, helping him with that, and then they needed to speed things up because I think their target time to market was pretty short, 6 to 9 months or something like that they wanted to get a working prototype out there in the field. We just pitched helping them with that.
But we found that the SOLIDWORKS model was pretty
Exactly. So I think the start of that was us working alongside them and him. And then came the niggles where we were kind of analysing different things. We had to kind of, as they were building it, things would have to get changed. And we kind of knew this already, but it became apparent that the way this draftsman was modelling things was not the right way. It was kind of smash CAD. It was not conducive to on-the-go changes and even looking at a version 2 later down the track, which was, I think, always in the plans for them.
But this happens as well because you're trying to create something conceptually from hand sketches or whatever, something that's in someone's head, creating smash CAD and then trying to then go to production or create a couple of prototypes. So having to go back to the drawing board is not necessarily a bad thing in a way.
The intention for them was to always have someone that could help them get the prototype working and provide the manufacturer packages for that, but also to streamline the process of refining things, doing V2s, V3s to kind of cut costs down later down the track.
But we had a number of our guys stationed in their workshop for 6 months,
6
maybe
to 12 months, I think it was.
which was great.
Pretty much full time.
Yeah, the guys were on the ground with the boilermakers, fitters, different things like that, different trades, and basically getting their direct feedback, making changes on the fly, coming up with new solutions.
Yep.
Next day, something, new parts come in, they're working on it together.
So that was definitely a case of us spending a bit more time up front, knowing their plans and their intentions to kind of get a good baseline driving part, if you like, with all those nicely laid out sketches that could then be changed and tuned down the track. So we did that, and we did it in a much nicer way that was conducive to them,
scaling
scaling the whole thing, I guess.
That's leveraging on our experience for trying to get people to market. Doing things in a certain way gets you to a certain place. SmashCAD in this particular case used SmashCAD to get an initial concept up, but going from an initial concept to then going to a manufacturable pre-production model, you may have to go back and do a bit more pre-work to be able to do that properly. To go to the next level and create different variants or have something that you can then refine using FEA, it's another different CAD modeling process.
We'd initially come up with our layout sketches. We would have to kind of lock in or agree on some sizes for the different toolboxes for all the different components, and probably everything was a bit oversized so that you've got more room than you need for that first version at least. Then to speed things up, we would kind of focus on each subsystem one at a time so that we could get that finished, approved, and they could at least start making the first ones before we went on to the next one. But that high-level layout was kind of already agreed between us and them, and we're comfortable that everything that had to fit on the back of the tray was going to fit. So this particular customer, didn't have anyone in-house. We were coming in as engineering consultants and then designers, and I guess they leveraged on our experience working with that, with all different CAD models, from tiny little injection molded tire pressure sensors all the way through to big structures, metal structures. And we've got a wealth of experience in especially welded steel structures. We were the engineering team, and we worked directly with them, integrated into their team to get them to market as fast as possible. And it's also an advantage for them as well. They don't have a ramp-up period. We already know what we're doing. They bring us in for that 6 to 12 months. I can't remember how long it was. And then they ramp it down, and you don't need to get rid of someone or keep someone on or whatever. We are going as fast as we possibly can to give the client the outcome that they want. And usually with these sorts of jobs, we know the timeframes and the costs. With bringing someone in who may not be skilled in that domain, and we've seen it many times before, they can drag on forever. And time is is the key. Training people on the job is one thing for longevity of a product or a project or a team. But if you want something done in a fixed time and cost, we've got enough experience to be able to do that now. That was one of a really, really good one for us, and they're still we're still doing all of their engineering. Continuous improvement is a massive thing for them. They've got 2 or 3 other variants that they've kind of spun off following that initial design. We up front kind of knew what their plan was, and they did have to get something out fairly quickly. So even on the design side, we could then guide them to spend the effort on the critical components that would have had the biggest impact on them failing those trials, you know what I mean? So making sure that nothing critical was going to happen. And there were things that didn't get analysed and down the track have failed maybe sooner than they hoped, but they weren't critical, and we addressing those as they go. So continuous improvement is a thing, but if we'd analysed everything from the start, that project probably wouldn't have taken it off.
Yeah, that's right. They would have missed their opportunity.
Exactly.
Wouldn't have got it out there, getting, effectively testing the tool. Maybe the structure might have been perfect, but you're not testing a tool. So again, horses for courses. The engineering program as a whole needs to be structured around what the end user experience is, or what the intention of the business is. You may have to take shortcuts sometimes, but that they're shortcuts. And as long as it's documented that shortcut has been made, and you need to go back and do it in a different way to satisfy the next thing, that's what you got to do as an engineer. Because at the end of the day, we're trying to do innovation as fast and cost effective as possible, and we want to see more innovation as an industry, especially local industry, and we all got to work together to do that, as long as we communicate it and document it.
Exactly.
That's all for today. Thanks to everyone for listening in. Feel free to like, subscribe, and leave a review. Have your say. Hot takes are very welcome. Until next time, make it good, make it fast. See you soon.